We're now ready to look at lateral dynamics. So again, we're going to start off with our linearized linearized lateral equations of motion, non-dimensional equations of motion. That's this set of equations here that we've developed previously. So these are the linearized equations. And we can, those are set up perfectly to plug in to this homogeneous set of solutions that can be used in our eigensolver. So this is the eigenproblem. And so we've got our two matrices here. We're actually going to, again, drop this matrix over here. This is from our control input. So we're going to drop that out and look at only the homogeneous solution to these equations, which is the solution that you get when you neglect control inputs or a forcing function. Okay, so this would be like the pilot control input. And so we're going to look at the dynamics of this aircraft without any pilot input. And so we've got these two these two matrices here that basically, again, if you look at these vectors here, if we know the current state of the aircraft, we multiply it by this, we can take the inverse of this matrix over and multiply it there, and that gives us the change in state for each of these parameters. Okay, so these are changes with respect to time. This is the current state of the aircraft, and from this setup of equations, we can then write out the eigenproblem, where this matrix here just gets plugged into here. So this is A minus lambda times B. So this is our B matrix from right there. We plug in, and we're going to get out a vector of an eigenvector and a set of eigenvalues. Okay, so an eigenvector for each of the eigenvalues. Now, after we've solved that, then we can, now that these solutions or these matrices are completely non-dimensional, that includes non-dimensional in time. And so in order to get frequencies and damping information from the eigenvalues, we need to redimensionalize the eigenvalue information that comes out. So for example, our damping is going to be minus the real of lambda multiplied by 2 v naught over b sub w. That's what we use to non-dimensionalize. And so now we're redimensionalizing to get sigma. The damped natural frequency is going to be the absolute value of the imaginary portion of lambda multiplied by 2 v naught over bw. And finally, the undamped natural frequency is, just a second there, is the square root of lambda 1, lambda 2 times 2 v naught over bw. Okay, so that's how we would redimensionalize information there in order to get actual frequencies and damping. So let's look at an example solution here based off of the same thing that we did for the longitudinal dynamics. We used this input file for this baseline glider, and so I'm using the exact same input file. It has all the information to compute both the longitudinal and the lateral dynamics of this glider. And so anyway, I can scroll through this, but these are all of the aerodynamic properties and also the mass properties up here of this glider, but then these are all of our aerodynamic derivatives that we've discussed previously about this particular glider. So let's now look at the solution here. So when I plug this, so I wrote a lateral solver that solved that eigenproblem, and so here's the A matrix here and the B matrix, and my solver that I wrote in Python accepts by default only a single matrix to do these special eigenproblems. So I need to take B inverse times A, so the inverse of this matrix times A, and then that gives me what I call C, and I plug that into the eigensolver, and out pop a set of eigenvalues and eigenvectors. So these are the eigenvalues that come out of this solver, and this is the set of eigenvectors, and of course there's one vector for each of the eigenvalues. Now, we understand that eigenvalues come out in pairs, right? So the first two are an obvious pair. Those are both exactly 0. And again, these are the rigid body modes of the aircraft, and we'll talk about those in a second. Next, I get out a real number here, and then two imaginary numbers that are complex conjugates. You can see that there. So these two obviously pair. So let me just mark these. So these two are going to be a pair. These two real numbers will be a pair, and then of course our two rigid body modes are a pair. So let's go through each of these and learn about these natural lateral modes that come out of this solver. So the first one is the first one I get is just a 0. This is a rigid body mode. So that's rigid body mode. And basically, again, that says that there's some value here. There's one of our independent variables that the dynamics really don't depend on the original value or the trim value or the equilibrium value, of that parameter. And so you can see we get a 1 right here. We have zeros outside of that for this eigenvector. And that 1 represents our y coordinate. So that's a non-dimensional y coordinate, remember? But basically it's saying that, it doesn't matter where you are located in the y coordinate. This is our y coordinate on the Earth fixed coordinate system. And so, of course, that shouldn't matter, right? Where we are in that y coordinate will not affect our dynamics. So that makes a lot of sense. Now, the second eigenvalue that comes out, also rigid body mode, it gives a -1 right here for that same y coordinate. So I see this every once in a while where it gives me the same rigid body mode out twice, and I'm not exactly sure why this is. I've seen this a few times though, where the rigid body modes it has a hard time with. I don't know if it's an ill-conditioned problem for solving for those or what, but actually what should happen is it should have come out for this mode or for this variable right here, and that's our heading. That psi value is a heading, and it shouldn't matter what direction the aircraft is heading, it will have the same dynamics. And so anyway, so in your solver you may get a 1 here for that for the y coordinate. You may get it for the heading. You may get a -1 for either of those. But anyway, just know that these are the two, the y coordinate and the heading are the two that are going to create these rigid body modes. And again, I just don't know what causes that. In some eigensolvers, I think those rigid body modes are maybe just a little ill-conditioned, and so sometimes you get slightly different results. But those are the two variables that will create or are causing our rigid body modes, okay? Those two variables right there. Okay, so let's go on to the next dimensionless eigenvalue. We've got -15 and then zeros for the imaginary part. So this is a real number. We've got a damping rate of 73 and then a 99% damping time of less than 1/10 of a second. This is 6% of a second. So this is very rapid damping. So this mode is going to last for just a very brief moment, and we probably won't even feel it on the aircraft. So let's look at what's happening here. And again, the eigenvector information here tells us what's actually happening in this mode. Now, this is a real number, and so if we were to plot the response of this, it doesn't have any damping. It's just going to come back to some equilibrium value. If there's a disturbance, it's going to return to some equilibrium value without oscillating. And so let's look at these components here. So again, beta, so we want to compare like components in here. The largest component here is this P, so that's my roll rate. And we can compare that to our yaw rate, and you can see that's an order of magnitude larger. So a lot of roll, very little yaw. And then Y doesn't have something really we can compare to very easily. Beta doesn't either, but phi and psi do. So this is my bank angle and my heading. And you can see it's a very large change in bank angle, a rather small change in heading. So again, an order of magnitude difference between those. So this is what's called the roll mode. So the roll mode is very heavily damped, and it's really difficult to really pick up on an aircraft. In fact, pilots don't even often know that it's there, or are able to sense it. But basically, and we can think of this as a response to a disturbance, but it's actually easier to understand the roll mode when you use the aileron as a disturbance. So let's say that we're flying along in steady level flight, and we deflect the aileron and deflect it to maybe 5 or 10 degrees instantaneously. So we put in a step change in aileron, and then hold the aileron at that deflection. Then that's how we would actually measure this roll mode. And what happens is if we look at our roll rate, so this is P, we would start at 0. So at the moment we're at time t equals 0, we don't have any rolling rate. But if we instantaneously deflect those ailerons, then the aircraft will begin to roll. Now the speed at which it ramps up to a constant rolling rate will depend on the inertia about the x-axis, and it will also depend on the strength of the ailerons, or the amount of control authority being produced by, or the rolling moment produced by those ailerons. But what happens is if we hold that aileron constant, our rolling rate will ramp up like this, and we've got a 99% damping time of 0.06 seconds here for this example. So let's say that's about 0.06 seconds here so it will take about that long to get up to a steady rolling rate, okay? So if we were to look at our bank angle, what happens with our bank angle is that at time t equals 0, so we've got time here on this axis, and then here we'll look at the bank angle instead of the roll rate. What happens is that our bank angle would ramp up to eventually a constant or a steady change, a rolling rate. Our bank angle would be continuously changing at this constant rate. Now, anyway, so that's another way to think of this. Okay, so we experience this mode with disturbances, but it's easiest to think about as a disturbance in aileron deflection, and that's how we would probably measure this experimentally. Is we'd put in a step aileron, and then measure the amount of time it takes us to get up to a constant rolling rate. Now, most pilots don't really notice that they have this time where they're ramping up, to a constant rolling rate. And so really they usually associate an aileron deflection with a magnitude of constant rolling rate. So, if they put in 5 degrees, then they're going to get up to this rolling rate nearly instantaneously. If they put in 10 degrees of deflection, then they would get up to a higher rolling rate nearly instantaneously. And so really they don't notice this much. There are some aircraft, though, where this can be pronounced, where this time can be pronounced. And usually those aircraft are those that have a lot of inertia around the x-axis. So, for example, I worked on the Stratolaunch program at Scaled Composites, and that aircraft has 2 fuselages offset from the center line and has a whole lot of inertia about that roll axis. And so it can take some time for this aircraft to ramp up to a constant rolling rate. Now, the reason the damping is so great here, see, this is, it's not common for this to be an oscillatory mode. And that's because the wingspan on aircraft are so great that you have so much roll damping. Remember, that's the CLP bar. So CL, comma P bar, that's our roll damping, and that's usually it's usually negative and large because our wingspan is so great that the lift distribution that's created by rolling the aircraft strongly opposes that rolling motion, and so anyway, you have large damping about the roll axis, and so anyway, this damps out rather quickly. excuse me, that's why the damping is so great here. So it's not common for the for us to have an oscillatory mode here. And we'll talk about what could happen there if we ever did have an oscillatory mode in just a moment. So anyway, this is the roll mode, and it's very heavily damped, usually a real number, and usually not a mode of concern necessarily for an aircraft. Okay, let's move on to this next set of eigenvalues. And this next set is our complex conjugate set. So we've got a negative number here. That means that it is convergent, but the fact that we've got an imaginary part here tells us that it's oscillatory. Okay, so we've got a convergent but oscillatory mode. This is going to take 1.4 seconds to completely damp out, and it's got a period of about 1.5 seconds, so actually nearly about the same. So we're going to see about one period of this before it completely damps out. And now let's look at the components here of what's happening here in this mode here. So we can look at this eigenvector and look at the relative amplitudes of each of these and the phase. And actually, the thing that stands out about this mode, now this mode is called the Dutch roll mode. This mode has noticeable components of basically all of the parameters. So if we look at P and R, for example, those are comparable parameters. We've got a 0.5 and a 0.2. So, one's twice as large as the other, but actually the other is not insignificant, right? So we need to realize that there's going to be changes in roll and yaw. We're going to have changes in our bank angle and our heading. Again, heading maybe a little bit more than the bank angle, but both of those are significant. We're going to have significant changes in beta and also significant changes in y. So actually, the thing that stands out about this mode is that actually there are really no terms that are insignificant here. All of these are coupled together. So like I said, this is called the Dutch roll mode. And the Dutch roll mode is usually oscillatory. And so if we look at it here, it will look something like that, and it will dampen out. Now, the fact that this one damps out, this particular glider is damped out in 1.5 seconds, I would say that's rare. Usually, if unless you have a yaw damping system on board, which we'll talk about later, if you just look at the natural aerodynamics of this aircraft with controls, with your rudder frozen and your ailerons frozen and everything, so you're not looking at any active damping on the aircraft, this can usually persist for some time. The damping is often relatively light, and the period, you'll notice, is actually right on the order of human response time, so about 1.5 seconds. Humans can usually respond to something in between 0.5 second and 2 seconds, and so we're right inside of that. And so we're going to talk later about handling qualities of an aircraft and how pilots rate aircraft, and the fact that the period of this is right on the same order as human response time can actually cause some problems, because what the pilot senses that they should do and what they actually should do to dampen out this mode can sometimes be two different things. So we'll talk about that a little bit later, but that's something to note, is that this mode can have can cause some issues because of the period, and it's usually lightly damped. So it usually persists much longer than 1.5 seconds. In this particular case, we've got quite a bit of damping for this particular mode. So we aren't going to see this. It's going to damp out rather quickly if we were to simulate this or actually fly this aircraft. But on most aircraft, this will persist for some time. So the Dutch roll is a combination of all these things. So we're going to have roll and yaw rates that are oscillating. So we're going to have oscillations in roll and yaw, and in our bank angle and in our heading. This kind of feels a little bit like fishtailing in a car. So where the back of the aircraft maybe wants to kind of pull ahead of the front of the aircraft a little bit, but then it oscillates, and then it'll move, it'll fishtail to the other side and go back and forth. But you experience that not only in yaw but also roll simultaneously. So Now we could look at the phase angles here, and you could figure out, which of these are happening when. But anyway, some of these are kind of lightly out of phase, and anyway, it's just kind of this complex fishtailing type of motion. Now this motion actually, I believe, the name of this, the Dutch roll mode, came from ice skating, because this kind of represented kind of the movement that ice skaters did. They had kind of this certain movement that they would make back in the day, and the Dutch were really good at ice skating, and so as I understand it, that's where the name of this mode came from, is kind of this oscillatory motion that some of the ice skaters would go through. So anyway, this can be a very dangerous mode for an aircraft. We'll talk about that a little bit later, and also other ways to control this mode. But that's where, so this is our second dimensionless, or excuse me, our next dimensionless eigenvalue, and of course it's got the counterpart here, the complex conjugate. So that's the Dutch roll mode. And so now let's move on. We had one more real. Remember, this real number pairs with this previous roll mode. That was a real number. And so we know that there's another real number in here, and that's our final dimensionless eigenvalue here, is also a real number. Now this actually is a positive real number, and so in our case, this is a divergent mode. Now, that's not true on all aircraft necessarily, but on this particular example, it's divergent, and so this could be a convergent mode or divergent mode, but it's real. Usually it's real, and so it's not. That means it's not oscillatory. Okay, so here we've got a divergent mode, and for a divergent mode, instead of reporting the 99% damping time, which we can really only do for a convergent mode, instead we can report the doubling time. So this says if we compute from the damping rate the doubling time, it says it takes about 1.4 seconds to double in amplitude. So that can be a little bit dangerous here. We'll talk about that in a moment. So let's look at the components of the eigenvector to try to figure out what's going on here. And you can see that there's one component here that is very dominant. This is a change in y. And then we can also look at the differences between P and R. So we've got a 3 times the change in R from P. So this is so that we've got a bit more yawing moment than rolling moment, but rolling moment is not insignificant here, right? So it's going to be a combination of the two with a little bit more a little bit more yaw than roll, and then bank angle and heading. Again, we've got about 3 times the amount change in heading as we do in bank angle. So this mode is called the spiral mode. And it is it's basically characterized by a change in heading of the aircraft. And what happens is the aircraft is flying along, and it gets a disturbance, a lateral disturbance, and it will go into this spiral motion. And actually, it will, if left unattended, it will continue to tighten and speed up, and as it changes heading, so this is a constant change in heading that we're seeing over here, right? We knew that we were going to have a change in y and also a large change in heading, but also we're going to have a change in bank angle, and so we had this change in yaw rate, which is creating our change in heading, but also a change in rolling rate. So as we move along, the aircraft is going to increase in bank angle and in rolling and yawing rate, and so this spiral will actually tighten, and if left unattended, this can be very dangerous for an aircraft, because it's picking up speed and it's tightening this turn and increasing the bank angle, and anyway, basically can end up in a spiral headed towards the ground. So at first, what this feels like is a little bit like a car with its alignment off. So if you've been driving down the freeway and let go of the steering wheel and your car drifts just slightly, That's how your alignment's off a little bit. You're going to drift away, and so that's kind of what it feels like to the pilot in this initial stage here. And most pilots are going to naturally correct that out. They're not even going to think about just keeping the aircraft going in a straight line, or an autopilot that's very simple for an autopilot to do. And obviously we do it as we drive cars all the time. We don't even really think about it. We just keep our car in our lane. And so this isn't necessarily a really dangerous mode. The times when this mode can be dangerous are if you lose visual a visual on your orientation. And so, for example, if you fly into a cloud and don't have the proper instrumentation, and so you can't see how you're oriented, because as you begin to bank and go into this spiral mode, you won't necessarily feel a very large change in your G loading on the aircraft. You won't be able to feel necessarily that the aircraft is banked and that you're entering this spiral, and so you can then fly out of the cloud in a completely different orientation than you were expecting, because it's not something that you can really feel on the aircraft. Okay, so for our example here, our doubling time is 1.4 seconds. That's not very long. So our drift here is going to double basically from our original steady level flight, or our equilibrium flight condition here. We're going to drift and double the amplitude of our deviation every 1.4 seconds. So that's rather quick. Now, most aircraft have a spiral mode that is either lightly divergent or lightly convergent. Okay, so this number is usually small and either could be positive or negative. Positive is going to be divergent, negative will be convergent. But this real number here tells us the damping, how much damping there is, and usually that's a rather small number, especially compared to like our roll mode. This is 2 orders of magnitude or 3 orders of magnitude smaller than the damping of the roll mode. So the roll mode has a whole lot of damping. Spiral mode has very light damping and can be either convergent or divergent, and really it's not too dangerous if you have a pilot on board. Now for a glider, if you don't have any controls on that glider, then of course you would want the spiral mode probably to be convergent so that your glider doesn't naturally go into this spiraling motion here. So anyway, so this is, again, the spiral mode. Now, the spiral mode and the roll mode are coupled, right? So they are mathematically coupled. If we come back up here to our list of eigenvalues, remember these are our 2 rigid body modes. Right here is the Dutch roll mode. And so we have the roll mode and the spiral mode that are mathematically coupled. Somehow the mathematics of those are coupling in our dynamic system of equations. But usually, because of our roll damping is so large, usually these are 2 real numbers. Now, there are some aircraft that have really stubby wings, really small wingspans, and it's possible that if your roll damping gets small enough, that these 2 can actually form an oscillatory coupled mode. Your roll mode and your spiral mode can actually combine and come out as some oscillatory or a complex conjugate and be some oscillatory mode. But that's not very common. That's kind of they would call that the lateral phugoid. If that happens, the Dutch roll is comparable to the short period in longitudinal. And so when these 2 couple, you can have a really slow oscillating lateral motion that they would call the lateral phugoid. But again, that's not very common. Most aircraft will have a real number for the roll mode and a real number for the spiral mode. Okay, so those are the lateral modes, and these are typical modes. Now, again, we're looking at glider values here for this particular example, and so some of these numbers magnitudes may be a little different than they are for conventional manned aircraft or other aircraft that you may be looking at. But in general, these types of modes are the types of modes that you'll get out of your lateral dynamics solver.